we left off with talking about quantum numbers and that our electrons are energy is based on how far away they are from the nucleus, what level away they are from the nucleus, and then what orbital they're sitting in. So orbitals deal with the quantum number m sub L. Okay, and each based on the probability density equation by Schrodinger has a specific shape. S orbitals, okay, are smallest and can hold 2 electrons. Okay, so S orbitals, every level has an S orbital. No matter if I'm a 1s, 2s, 3s, 4s, whatever I am, I hold 2 electrons. Okay, my shape is a sphere. Okay, so it's a 3D shape, XYZ coordinate. And the number of nodes, and what a node is, okay, node, a place where I won't find any electrons. The number of nodes is dependent on my n value. Okay. Number of nodes depends on what level I'm on, n minus 1. So, if I were an electron and I were sitting in the 1s, the 1s has no nodes. If I were looking at the probability density for the 1s orbital, it would look like this. It'd be all filled in, and again, it'd be a sphere, but it would be all filled in, and I'd have 0 nodes, because the number of nodes, the number of spots I would not find an electron would be, so this is the 1s, 1 minus 1. Okay? If I were in the 2s, I would have a 1s, but then I'd have an extra area around it. I'd look something like this. Okay, this is the 2s. This part is the node, where I won't find any electrons. Okay, and how many nodes should I have? Well, I'm in the 2s. 2 minus 1, all right, is 1. So I have 1 node. Move on to the 3s. Okay, we have this, and then we have this, and then we have this. Okay. And I have 2 nodes now. An area here where I won't find electrons, an area here I won't find electrons. And the thing is, what you have to realize is that as we move up our n levels, as we move up our electron shells, our nodes our orbitals for the s get bigger and bigger. Therefore, if I'm getting bigger and bigger, there's more area for my electrons to be, but as long as there's more area for electrons to be, there's also more area for electrons not to be. Okay, this one here. We got 1, 2, and then yet another one. And this would be the 4s. And 4 minus 1 is 3, so we should have 3 nodes, and we do. Node, node, and node. Okay. So our s orbitals are spherical. Okay. And as they get bigger, there's more spots for electrons to be, but there's also more spots for electrons not to be. And this is what this slide is illustrating. Our p orbital. Okay. In our p subshells, there are 3 p orbitals. Therefore, a p orbital or a p subshell, each orbital can hold 2 electrons. The p subshell will hold 6 electrons total. When we look at the probability density, they form these dumbbell shapes. So this is one p orbital where 2 electrons could sit. Here's another one where 2 electrons can sit. Here's another one where 2 electrons. So 2, 4, 6 electrons total. They only have 1 node. Right there. Where the bow tie slash, or where the dumbbell, I should say, meets. This area here is the node. No matter their size, the node doesn't increase like an S with the sphere. These may get bigger, but the node is always the center that's linking them together. Okay. So, dumbbell shaped, holds 6 electrons. The D and the F get more and more complicated. The F is extremely complicated. The D, each one of these, there's 5 D orbitals in the D subshell. Each one of these essentially looks like 2 p orbitals on each other, except when you get down to what they call the bow tie, has one node again. Right there. Now the D is not seen until you get to level 3. Okay. Therefore, the D orbitals could hold 10 electrons. And the F we don't even have a picture of, but the F can hold 14 electrons because there's 7 different orbitals in the shell. Okay. So this talks about their shape. Well, here's the deal. When our atoms are arranging their electrons, they will fill from the lowest energy to the highest energy in that order. So the electrons will sit, and your book uses boxes. A lot of books use lines. An electron is represented by a half arrow. Okay, that was an awful half arrow there. But electrons are represented by half arrows, either pointing up or pointing down. You can use the boxes if you like. You can use a line if you like. So we're going to fill from our lowest amount of energy to our highest amount of energy. Okay? And we'll keep filling till we run out of electrons. I want to show you here that the 3D is actually higher energy, even though it's at a lower energy shell than 4s, because the amount of orbitals. As we get further and further away from the nucleus, our electron shells get closer and closer and closer together. The 3D and 4s are so close together that the 3D actually fills after the 4s, even though this is at a higher level, because these 5 orbitals take precedent over the 2 or the 1 or ability to hold 2 electrons in the 4s. Well, how do I know what fills, how it fills, what's going on, and all of that? Okay, we talked about electron spin last time, and I talked about Pauli exclusion. Okay. So, there's a couple rules here. All right? When writing what we call the electron configuration. Number 1, we have to start from our lowest energy to our highest energy. Number 2, okay, electrons that are filling and in the same orbital have to be opposite spins. That's so that they have the 4 different quantum numbers, which we talked about last time. And last, I can't pair up electrons until each orbital in a subshell has 1. And that's known as Hund's rule. Okay. So, here's the way that I found it beneficial to learn. I'm going to show you 2 ways. This is known as the picket fence way, and there's also the periodic table way. I like the picket fence way because it's essentially as long as I know how many electrons each orbital or each subshell can hold, I'll be okay. You follow the arrows. The 1s fills, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, 4p, 5s, 4d, 5p, 6s, 4F5D 6P 7S, and so on. You just follow the arrows. The key is you have to know how many electrons each one of these holds. Anything in the S can hold 2, anything in the P can hold 6, anything in the D can hold a max of 10, and anything in the F can hold 14. So how does this all work out? Well, it works out like the following. Let's say I want to write the electron configuration for sodium. Okay, so I look at sodium on the periodic table. Sodium has 11 protons, therefore a neutral sodium has 11 electrons. Okay, so I've got to fit 11 electrons into the electron shells. All right, so let's take a look. The first one to fill, according to our picket fence, is the 1s, and the 1s is going to hold 2 electrons. Next, the 2s will fill, and it'll hold 2 electrons. Following that, the 2p, which will hold 6. So I've got a total of 10 if we count 1s2, 2s2, that's 4 plus 2p6, so I need one more electron. And my electron configuration would look like this. 1s2, 2s2, 2p6, 3s1. And we can write it shorthand too. 1s2, 2s2, 2p6, 3s1. This is showing the complete diagram. This is the shorthand, one of the shorthand ways. Let's look at another one. Let's do fluorine. Okay, fluorine has 9 electrons. The 1s, according to our little map there, fills first, then the 2s, that's 4, then the 2p. And I need 9. So 1, 2, 3. Don't pair them up until you have to. Got to pair it up. Opposite spin. Got to pair it up. So this is what fluorine would look like. Or 1s2, 2s2, 2p5. Okay, and this is known as the ground state electron configuration. Now, let's look at neon. Okay. Let's look at neon. Neon has 10 electrons. Therefore, all right, 1s2, 2s2, 2p6. Okay. All right. So that's what we have. Now, if we go back to our ions, okay, neon is a noble gas, not going to have an ion. Fluorine's in group 17. Fluorine's going to want to do what? Fluorine's going to want to gain 1 electron. And if fluorine minus, we'll do it over here. Let's do it over here. Fluorine minus, okay, would have 10 electrons. 9, based on the periodic table, plus the minus 10 electrons. Fluorine would be fluorine minus as an ion, 1s2, 2s2, 2p6. Okay. Sodium positive, all right, as an ion, sodium is in group 1, wants to give up 1. What 1 is sodium giving up? Sodium is giving up that one. So sodium positive would be 1s2, 2s2, 2p6. And notice something, that sodium positive as a cation and fluorine negative looks just like neon. And if you remember when we talked about our ions, the whole goal was to look like a noble gas. And here's how they look like a noble gas. They look like a noble gas by giving up or gaining the electrons to look specifically like the noble gas. For my anions, the noble gas that's coming up. For my cations, the noble gas that came before me. Okay. So, that being said, keeping neon down here, there's actually a shorthand way, an even shorter way, to write electron configuration. Okay. And the key is this. Find the noble gas that comes before. So, 1s2, 2s2, 2p6. That's neon. Write it as neon and then whatever the leftover extra is. 3s1. And that's another way of writing this electron configuration to show how the electrons are being added. For fluorine, well, it doesn't have neon in it, but it has 1s2. So this is helium. So we would write fluorine out as helium. Okay. 2s2, 2p5. The noble gas that's in your electron configuration plus the extra. And this is known as the noble gas configuration. Okay. So you could write it out this long ways. You could write it out the shorthand way. So let's look at another one. Let's do calcium. Calcium has 20 electrons. Okay, so let's look at calcium. Calcium has 20 electrons. I know this by looking on the periodic table, looking at the atomic number, which tells me the number of protons and therefore tells me the number of electrons as long as I'm neutral. Okay. If we go back to our picket fence, okay, so the 1s is going to hold 2. The 2s is going to hold 2. The 2p is going to hold 6. So there's a total right now of 10 electrons. Then the next to fill is the 3s. It'll hold 2. Then the 3p. And then, not the 3d, but the 4s. Okay, so follow that line, and the p fills of the 3, and then the 4s. Okay. So, it looks like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. Now I want to write it the noble gas way. Find my noble gas configuration. So if I look at the periodic table, argon comes before calcium. Argon has 18 electrons. Here is argon right here. So I could write this as argon 4s2. Okay? Questions on this? It's pretty much straightforward. Follow the arrows, and as long as you know the number of electrons, and I'll show you how to use the periodic table. You can use that method too. But just like everything else, there is exceptions to the rule. First thing, follow your pathway. Follow the correct pathway and you're good to go. But let's look at silver. Silver has 47 electrons. Okay. Now we're going to start to do this. All right, so 1s2, 2s2, 2p6. Okay, that's 2, 4, 6, 8, 10. So we're down to 37 electrons. All right. 3s2, 3p6, 4s2. All right, so we got 2, 4, 6, 8, 10 more. Down to 27 electrons. According to our picket fence. Okay, now we're going further out than we ever had before. Our next thing to fill, so we did the 1s2, we did the 2s2, we did the 2p6, the 3s2, 3p6, 4s2. Now we're on 3d. Okay. We are now right here. So 3D is going to hold 10. So 3d10, that leaves us with 17 electrons. What comes next? 4p. Okay, so 4p is going to hold 6. 1, 2, 3, 4, 5, 6. That leaves us with 11 electrons. Then comes 5s2 and 4d10 will have 9 electrons left. Okay, so it'll look like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. And here's where the exception comes into play. If I fill my orbitals in the correct order, and I end up with an S2 and a D9 or a D4, where I'm either completely filled or I'm only half filled. Okay, one away from being completely filled is what I should say, or one away from being half filled. What will happen is this. So what I always tell students, write it out like this, then look. Do you have this situation where there's an S2 with a D9 or a D4? This electron will get moved from the 5s to the 4d. And silver's real electron configuration isn't 4d9 5s2. It's 4d10 5s1, and that's why silver's always a +1 charge. So write it out normally, follow your picket fence normally, then look. Do I have a D that's half filled or one away from being half filled or one away from being completely filled? I could take one electron from the S and completely fill it. It just makes the atom more stable. You can't take two. It's only one, and it only happens if I'm one away from being half filled or one away from being completely filled. So, on that exception, we could build off that and say, well, what if you were asked, what is, all right, what if this was the question? What are the 4 quantum numbers, okay, for the electron, okay, that makes silver turn into silver plus. Okay, so what they're asking you here is, what are the quantum numbers of the electron silver is going to lose to become silver positive? Well, it's not going to lose any of these. It's going to lose this one. So to answer this question, we would say, well, we're on the 5th level, so it has to be n equals 5. My L is 0 because I'm an S. My M sub L is 0 because I'm in an S. And my M sub S, you pick. You want plus a half, you want minus a half, whatever one you want. Okay. And your book does a couple homework problems like that. It'll give you something like, for instance, here. Let's look at chlorine. All right, chlorine, it has, 17 electrons? Yeah, 17 electrons. Chlorine is a 1s2, 2s2, 2p5, or 2p6, sorry. I'm thinking fluorine as I'm writing chlorine. 2p6, 3s2, 3p5. Now, if you go back, okay, and this is going to tie everything together, and you should be extremely excited, as I get excited doing this. If you go back and we said, okay, it has 17 electrons, how many valence electrons does chlorine have? And if we go back to what we learned in Chapter 2, it has 7 valence electrons because it's in Group 7A or Group 17. Well, where are those 7 valence electrons? Here they are, my outermost electrons. Because chlorine would have a nucleus with neutrons and protons. It would have an n equals 1, an n equals 2, an n equals 3. So here we'd have 2 electrons. Here we'd have 8 electrons. And out here would be my 7 electrons in the n equals 3. So here are my valence electrons. Okay? Now, if the question said, what are the quantum numbers, I'm just going to put Q number, for the electron that turns chlorine into chlorine minus. So where would that electron go? Well, if I were an electron and I were going to become chlorine minus, the only spot would be in my valence shell. I would go here. This would be the one to make it Cl minus, or to look like argon. So what would my quantum numbers be? Okay, my quantum numbers would be n equals 3. I'm on the 3rd level. My L is 1 because of the P. So here's my L. Here's my N. These are -1, 0, and 1. Compare it again to my quantum numbers. M sub L. So it would be a +1. And then what would my spin be? You pick. I'm going to say plus a half. It doesn't matter. You can put minus a half if you want. Okay. If I wanted to write chlorine in the shorthand way, chlorine by itself would be neon, 3s2 in the noble gas way, 3p5. If I wanted to write it as this one, it would be neon with a 3p6. So your electron configuration, how my electrons are arranged, can be figured out for every atom following this picket fence. But it could also be figured out by looking at the periodic table. And your book uses the periodic table way. And that's fine. I like to use the periodic table as a double check to make sure I'm in the right church. But you do it however you're comfortable. I know a bunch of students said they learned in high school the periodic table way. All right? And this is just showing you the differences in the stuff we talked about here. But let me get to that periodic table. And you could, as long as you know how many electrons each one holds, the periodic table can help you. Just by looking on the periodic table, this has to be a 1s. This is 2s. 2s1, 2s2. So this is 2s1, 2s2. 2p1, 2p2, 2p3, 2p4, but everything else behind it you have to remember. So the electron configuration, I would say, okay, this is 2p6. All right, and everything else in this is going to be a 6, things like that. All right, I would say, okay, what comes before it? So a 1s2 completely fills, a 2s2 completely fills, and then I'm a 2p what? This would be 3d1, 3d2, 3d3, 4, 5, 6, 7, 8, 9, and 10. It's a terrible 8. 8. Okay. And same thing down here, 1 through 14. All right. 4, 5, 6, 7, 8, 9. So my lanthanides and my actinides are the ones that have the f orbitals. 12, 13, and 14. And this goes all the way down. So if I go here to argon, argon would be a what? 1s2, a 2s2, a 2p6, then a 3s2, and if I was looking right here, 3p6. What if I wanted to look at, something below here? Maybe we got what? Chlorine, bromine. What if I want to do bromines instead of following the picket fence? All right, if I understand the periodic table method, this is a 1s2, 2s2, comes all the way over, 2p6, 3s2, 3p6, then a 4s2. We come all the way across the 3d10, and this is a 1, 2, 3, 4, 5. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p5. Some people find that easier because if you have the periodic table, it's right there and you can use it. Either way will get you to the right answer. You should be able to write it the longhand way. You should be able to write it with the boxes. You should be able to write it in the noble gas configuration. Adding and removing electrons, and here's that, those examples that I told you. Instead of being 3d10 4s1, instead of being 3d9 4s2 for copper. Chromium is 3d5 4s1 instead of being 4 and 2. Write it out normally, then go back and double check. If there's an S that's one away from being, or a D one away from being half filled or completely filled, it'll steal one from the S. The last terms we need to talk about are paramagnetism and diamagnetism, which means, am I affected by a magnetic field or am I not? When I write out the electromagnetic spectrum, the electron configuration, if I have one or more unpaired electrons, I should be attracted in a magnetic field. If I don't, everything's paired up, I won't have any attraction in a magnetic field. Paramagnetism meaning for magnetism, diamagnetism meaning against magnetism. So for means I'll be affected, I have an unpaired electron. Diamagnetism, I don't. Okay? And that's really what we did in that half hour is what your book keeps as chapter 8. Okay? And that's why I sat there and said, well, why did they change chapter 7 and take the electron configuration out and put it in its own separate chapter? Because it's really like 8 pages. And the reason is that they could sell a new edition to the book, if we're being honest here. Okay? They include atom size and stuff like that. We'll talk about that in Gen Chem 2 for those of you who have to take Gen Chem 2. Okay. So, homework that deals with this. We are on page 363. .11 to 8.14. .21 to 8.42. Okay. Where it says draw ground state and things like that, don't worry about that. Just draw the molecular electron configuration diagrams out. if they're asking in this partial valence orbital diagram, they want the lines or the boxes. Okay? That's what they call the lines and the boxes. So if they're asking you to draw a partial valence level orbital diagram, that's what they want you to do. The ones that are asking you how many inner, outer, and valence electrons are present, which is 8.37 and 8.38, you could skip those. Skip 8.37 and 38. Okay. All right. Let's see. Tuesday, Thursday. All right. So your final is, again, Tuesday, May 12th, 12:30 to 2:30. Blackboard. Okay, you'll be able to access the exam from 12:30 to 12:50, and you'll have 2 hours to do it. Same format, and it's only on Chapter 7 and 8. It's only on this PowerPoint presentation. All right. Same kind of format, multiple choice, problems. All right. I mean, I can meet if you guys want to. I mean, your final is when class would be on Tuesday, so. But I'll leave that up to you guys. I mean, if you want to meet, I can meet. I could do... Trying to think of my schedule on Monday. Yeah, Monday night should work. Monday night could work. Put a post on the discussion on Learn. There's videos on Blackboard on this too, don't forget, guys, to help you out there. I don't know, 7 o'clock, 8 o'clock, 7 o'clock, 8 o'clock, in and around there. Just leave me a message and I'll respond to it this weekend. Unless you guys want to go earlier at like 5, but I figure some of you might have finals.